All right. Well, welcome everyone to this webinar. And we have here Jack Reeves Eyre, I hope I pronounced that right, who's going to talk to us about the much overlooked diurnal variation of the marine temperature and the role that atmospheric tides have in it. And go ahead, Jack.
Thank you. I'm going to just please shout out if either you can't hear me or you can't see the slides or anything like that, but otherwise, I trust that you can see and hear. But yeah, thank you. It's great to be here. Thank you for this opportunity to present this work. So yeah, my name is Jack Reeves Eyre, and my co-authors are listed here, and I want to particularly highlight Jessica Caggiano, who is the lead author on the paper, and has kind of been the reason this has been published and we started this in the first place. Yeah, before I get started, I'll just kind of explain the branding on these slides. So this is my current affiliation. I work at the Office of Coast Survey at NOAA, where I work on storm surge model skill assessment. That is not particularly closely related to this work, but that's just kind of the reason that I have these logos and words on the slides. But yeah, this is work that was started. Actually, let me go to the next slide and then we can. Okay, let's move on. So this is work that came out of a La Penta scholarship. That's a NOAA program that Jess was part of in 2023, and then the work has continued since then. And that's work that I did while I was at the NOAA Climate Prediction Center with other colleagues there and colleagues at Pacific Marine Environmental Lab in Seattle, including Megan Cronin, who I probably assume most of you here will know. In fact, Megan may be here, I'm not sure, but let's see. Yeah, so that's the kind of the group of co-authors on this paper, and excitingly, it's just been published a few weeks ago in GRL. The slides here have links in them, so I don't know if it's possible to share them afterwards, or I mean, it's pretty easy to search. You know, the title of this presentation will probably get you to the paper on Google without much difficulty. So that's the background, and then the kind of scientific starting point for this work was some research that I led, again at the Climate Prediction Center, using a model that had increased vertical resolution in the ocean component. And what we found was that allows the model to accurately simulate the temperature, the sea surface temperature diurnal cycle, and a few other features in the upper ocean. So that's where we kind of started back in 2023 on this work. And so just to go a very brief background on that, because it kind of sets the scene a little bit. Most global climate models that are used for kind of long-term simulations have vertical resolution in the upper ocean of order 10 meters. We used a model called CFS, Climate Forecast System, and then the suffix on that is M501, which meant it's MOM5 with a vertical resolution of 1 meter in the upper ocean. So that meant that it's able to capture the sea surface temperature diurnal cycle and current diurnal cycle. So in places where there's strong solar radiation and relatively light winds, the upper 2 to 3 meters of the ocean can heat up quite notably during the daytime and then cool down at night. And that also shows up in the ocean currents as well. So there's a few figures here. I won't go into details on those, but it's just to kind of note that there is other work that explains that. So yeah, that's the kind of the ocean focus of using this model. The remaining question after that work was, what about the atmosphere? And that's where Jess's internship a couple of years ago picked up. So the goal of that project was to use the same model, CFS M501, to explore the diurnal variations of air-sea fluxes and the atmosphere, the marine atmospheric boundary layer in that same model. And yeah, so I'll go over kind of data and methods first, and then we'll come back to exactly what we're interested in looking at in a couple of minutes. But yeah, again, the model, like I just said, is the CFS M501. It's a coupled ocean atmosphere global model. The ocean is MOM5, and that vertical resolution is up to 1 meter. It's 1 meter for the top 10 meters of the ocean, and then kind of gradually decreases further down. We used a free running simulation, no data assimilation part of that. It was a 26-year run, and we had 4 years of that where we have hourly output, global hourly output. But we're just going to focus on locations of tropical Pacific TAU moorings, and I'll show you those locations in a minute on another slide. But rather than kind of look at a whole global version, we're just kind of looking at these discrete locations that have been relatively well studied in the past. Methods, this is a little complicated. We'll kind of come back to it as we look at the data, but I'll kind of give the overview now. We're looking at something called the diurnal composite. So that's a multi-month and or multi-year average separately for each hour of the day. So we have a kind of multi-month, multi-year 0 UTC average, 1, 2, 3, right through the day up to the 23rd hour. So those 24 daily points averaged over multiple months and years. And then on top of that, we can convert that to an anomaly, diurnal anomaly composite, by subtracting the mean of that. So the mean across the 24 values, subtract that, and then you will get this kind of daily variation around 0. And we denote that by this delta symbol. So when you see that in the upcoming slides, that's what that means. It's the diurnal anomaly composite. And the quantities that we're interested in. So like I said, it's kind of fluxes and marine boundary layer, marine atmospheric boundary layer are the area we're looking at. So that means air temperature, humidity, wind speed, air pressure, and sensible and latent heat flux. They're the primary things we started out looking at. And the starting point is the marine air temperature. This is, the title slightly gives it away, but the marine air temperature is going to be the focus here for this slide, but also for most of the talk. It's the kind of the leading result that we have. But let me describe this figure first, and then we'll come back to the text. So on the left, we've got a map of in the middle, the map of the sea surface temperature diurnal range. So that means the kind of the lowest to the highest value in that diurnal anomaly composite. And so we see large values over close to the Galapagos Islands, around 1 Kelvin, and it kind of varies across the equator, and then the lowest values are in just north of the equator. But yeah, there's a considerable variation across the tropical Pacific. And then around that, I've picked out 6 different locations to show the time series of the SST and the marine air temperature. And the SST in each case, there are different ranges across the different locations, as you'd expect from the map. But the pattern of variation is consistent across them. So a minimum around 8 local time, and a maximum around 3 or 4 local time, and a kind of monotonic variation between those two. The air temperature is quite different to that. It has an earlier minimum in all of these cases, so around 3 to 4 local time AM. It has a late morning, either secondary maximum or a kind of a slowdown, depending on which locations we're looking at, and then an early afternoon secondary minimum in some of these cases. And then in 1 or 2 cases as well, the marine air temperature range can be greater than the SST range. So particularly the ones in the upper left here, the marine air temperature varies more than the SST. So this is all to say, really, the key result from this is that the marine air temperature is not just following the SST. There's clearly other physics going on here. Before I go on, I'm going to just pause and say, if anyone has questions, then it's a little hard for me to see the screen and what else is going on around here, but please just kind of shout out if you have questions or need clarification on anything. We can save more general questions for the end, I guess, but if there's anything that needs clarifying within a particular slide, then please just let me know. But yeah, otherwise I'll move on. So
I'll let you know if anybody lifts their hands, I guess, online in the meantime.
thank you. I appreciate that. Okay, yeah, so we see that something else in our results from the model, something else is going on. So the starting point now is the literature. What's going on with, what have people observed with marine air temperature diurnal cycle in the past? And there's two main areas that I've kind of color coded here. One is related to climate monitoring, and one is to do with instrument biases and their correction. So in green, climate monitoring kind of has a few angles on marine air temperature diurnal cycle. First of all, I will point out that long-term global temperature products, the kind of ones that are used to say, you know, this is the warmest year on record, those kind of headlines will often be based on these global data sets. They tend to use SST instead of marine air temperature over the oceans. And that has a kind of implicit assumption that the diurnal cycle of the marine air temperature follows the diurnal cycle of the SST, at least in a kind of long-term average sense. So this link here is a fairly recent paper that kind of has some insights on that. And there is a kind of recognition, I think, that that is not totally correct, but at the same time, just the data shortcomings mean that that is a much more kind of reasonable thing to do. Another climate monitoring results that we see is that global marine air temperature data sets, not that they're as kind of well known as these big global climate monitoring data sets, they use only the nighttime marine air temperature, and that's due to assumed daytime heating biases. And so let's go on to those next. So that the main results that we've kind of looked at in relation to this paper are this study from 1998, Anderson and Baumgartner, who compared unaspirated thermometers, which are the most common type in marine applications, compared those with aspirated and found that unaspirated have a daytime warm bias. I'm going to come back to this and give some more detail in a minute, but let's just start from that. Other studies related to this, so we've got kind of two other relevant studies, Berry et al. 2004 and de Rivière et al. 2022. They're kind of making assumptions within them that either delta mat is equal to delta SST or it's equal to 0, or somewhere in between those. So these are kind of either assumed or kind of bounding assumptions of how the marine air temperature varies during the daytime. So I think that we can kind of dig into the details a little more if we need to, but the key point here is to say that a lot of these are assumptions rather than kind of directly known facts, kind of with observational evidence. I think the key one, which I'll come to next, is this unaspirated versus aspirated thermometers. But still, even with that result, we found that there's not a lot really known about the marine air temperature diurnal cycle. So yeah, let me go into a little more detail on this Anderson and Baumgartner 1998 study. So like I said, it compared aspirated, by which I mean there is essentially a fan within the thermometer shield that keeps the air moving through there and stops or reduces kind of warming bias of the thermometer surroundings. Comparing that kind of that style to unaspirated thermometers, they have not a very large data set, but it's all there is, and it's better than nothing. So one buoy in the tropical Pacific that had a 13-day time series, and then a couple with 50 or 60 days from the Arabian Sea. These are both kind of low wind, high solar radiation environments that have therefore quite large diurnal cycles of SST. And the results I'm showing here are the kind of mean diurnal cycles, similar to what I'm going to show later on. So these are the diurnal variations from these different locations averaged over the time series. And so the kind of lowest down black solid line is the aspirated, which we kind of take as the truth, or as close to it as we can observe. And then the above that, the kind of the top line is the SST, the dashed line in each case is the SST. And then these other lines that kind of in the nighttime follow the aspirated air temperature, but then in the daytime have these kind of positive deviations from that. They're the unaspirated sensors that we're interpreting here as having a bias compared to that more accurate aspirated thermometer style. So there, I think this is kind of pretty clear evidence that there undoubtedly are some sensor biases from between these two different styles of sensor. So anything that is based on unaspirated, unventilated thermometer is going to have some daytime warm bias. But as well as that, these observations do kind of have a couple of interesting similarities with our model results, including the early morning minima that is quite a bit earlier between these three locations, quite a bit earlier than sunrise. So the temperature reaches its minimum at roughly the same time as we saw in the model, and then starts going up again before sunrise. And then it's a little hard to see in all of these cases, but potentially there is a late morning maxima, or at least a late morning slowdown or kind of plateauing of the temperature. Whereas the SST keeps warming till mid-afternoon, the air temperature warming in some of these cases slows down or reverses late morning, early afternoon. So there's definitely, yeah, the summary is there's two things going on. There is a temperature bias from an unaspirated thermometer, but also there are some unexplained physics going on in the air temperature variation. So I've got some details on these other studies. I don't want to go into too much detail just in the interest of time, but I will kind of say, yeah, let's quickly go over it. Berry et al. Constraining the radiative heating error. So looking at that same phenomenon from ships specifically, and constraining the heating error by saying that the true variation lies somewhere between 0, so no diurnal variation of the air temperature, and the other extreme where it follows the SST exactly. So that's kind of saying that the truth is somewhere in between those extremes. And using those assumptions, kind of quantifying the errors, they find average errors of order 0.3 Kelvin. This is a kind of a mid-latitude to high latitude station, so potentially the magnitude of things could be quite different. But again, it's probably a pretty safe assumption, safe result that there are some, especially on a ship where there's a lot of shielding and a lot of metal to heat up, there are biases from those sensors, but there is some uncertainty in the magnitude. And then this other study from only a few years ago, 2022, used a much kind of longer term and wider geographical range of data from the tropical Pacific, estimated the radiative heating error by subtracting the nighttime marine air temperature average from the 24-hour marine air temperature, which I think implies that they're assuming there is 0 marine air temperature variation, delta mat equals 0. I'm not totally confident on if that's a correct interpretation or not, but there is some kind of assumption within this method of quantifying the errors. And they're finding in these locations an average difference between these two of order 0.1 Kelvin, with some variation and occasionally, 0.5 or even more, but that's the average value. So just as a kind of, from these 3 studies, we kind of have an average or some sense of the magnitude of radiative heating errors on average. So that's the literature. Let's go back to our results now. And let's amend the project goal to say we do still want to understand those things more generally, but we do need to understand this marine air temperature diurnal cycle better. And so I've kind of skirted around this in those previous slides, but one key thing to look at is this difference between the SST and the air temperature. And so we're looking now at a figure that shows a lot of blue lines. Each blue line is 1 month and 1 location from those tropical Pacific, those green points on the map we saw earlier. And the black line is the mean of all those different blue lines. But even with all those lots of lines kind of overlaid on each other, there's a pretty clear, consistent semi-diurnal cycle. And the timing of this is also very consistent. So we're seeing the difference has maxima at roughly 3 a.m. and 3 p.m. and minima at 9 a.m. and 9 p.m. on average. I'll also note that this is not a kind of a normalized value. So this also reflects the actual temperature difference between the two in the model. So it is on average around 0.5 Kelvin. So the SST is warmer than the air temperature. But there are some situations where that's not true. So the air temperature can be warmer than the SST on average. And then there's a few close to zero where with that semi-diurnal rise and fall, the sign of the temperature difference actually flips twice a day as well, which is a kind of special case when your average is close to zero. But it's very consistent in the magnitude in most cases, and the timing is the same across all these different locations and different seasons as well. So to explain this, we're going to go back to 1918. This is a paper by George Simpson, who says, this is a little blurry, so let me read this. If the trace of a self-recording barometer from the tropics is examined, it will at once be seen that it forms a sinuous line having 2 waves each day. It will also be noticed that the consecutive maxima and minima occur with great regularity at the same time each day. The maxima occur approximately 10 a.m. and 10 p.m., and the minima at 4 a.m. and 4 p.m. So that's pressure. Barometers record pressure, air pressure, and that sounds a lot like what we just saw. So the next question is, do we have that in our model as well? Is this a related phenomenon? And we do have that. It's very, very clear. This is the diurnal composite anomalies of the air pressure from this model. Same kind of figure with all the blue lines from different locations and different seasons, and then the black line is the mean of those. And this is even more consistent than the SST minus MAT difference. The timing is extremely consistent. The magnitude is extremely consistent. Just like the timing is actually, I think, probably 1 hour different from the 1918 paper we just looked at, but that could potentially be to do with the calculation of local time or the assumption of time made earlier in the 1918 analysis. But otherwise, it's very similar to this kind of long known about air pressure variation. So what's causing this? This is it gets technical quickly, so I'm not going to go into great detail, but the short answer is atmospheric tides. So solar radiation is absorbed by the upper atmosphere, so stratosphere and above, and that causes temperature and pressure variations in the upper atmosphere at the 24-hour period and its harmonics. So there's kind of oscillations, 24 hours at 12, 8, 6 hours, any of the harmonics of the 24-hour period. And at the surface, the 12-hourly, so S2 harmonic is the dominant component. The 24-hour oscillation is not able to propagate efficiently down from the stratosphere to the surface. So the 12-hourly component is the dominant thing left over. Yeah, it's just worth pointing out, tides we probably all know better from the oceans, where they are mostly gravitational forced. This is a thermal forcing and is tied to the sun more than the moon, so it has an exact 24-hour period rather than the 24 and a bit hour gravitational period of ocean tides. So I'm going to move on. We could spend hours on this, but I won't. Let's go back to our results. But the key insight I want to share here is that this pressure variation can be related to an air temperature variation using the first law of thermodynamics and the ideal gas law. So this is kind of pretty basic so atmospheric science result that you can kind of calculate between these things, air temperature and pressure variations. And so we kind of have this, we can calculate a predicted air temperature change from a pressure change using these laws, and we get this kind of result from this equation here. And then if I calculate this from the model's pressure field and do the same kind of figure, this is what we get. So marine air temperature variation, very consistent, timing and magnitude. And the magnitude is, of order 0.3 Kelvin. As the kind of the peak to peak range of that variation. So knowing that that's kind of one contribution to how the air temperature can change, we're now going to look at what we're going to call a parameterization, which is kind of asking which one is a better reflection of the model air temperature. Is it better represented by just the SST variation, or SST variation plus this adiabatic pressure forced variation as well? So in this figure I'm showing these, we've got the blue line, the black line is the model's true air temperature field, as it comes straight out of the model. The blue line is the SST, and the red line is the SST plus adiabatic parameterization. And this is just one season, or 1 month, sorry, and one location. And we can see here, I think it's pretty clear that the including the adiabatic component results in a better parameterization than just assuming that the MAP variation follows the SST variation. So in both the magnitude and the timing in this location, it seems like the red line is closer to the black line, basically. So we want to generalize this kind of result. This example is a good one, but we want to see how representative is this of the general case. And to do that, we're going to look at a couple of different quantities, which we can kind of think about in terms of this figure. So one is the mean absolute error across the 24-hour cycle. We compare the error between the red and the black line as one, the kind of SST plus adiabatic mean absolute error, and then the error between the blue and the black lines is the other. And we want to see, okay, which one of those has the least error. So that's a kind of a magnitude focused component. The timing also is important. And so we have a kind of the same kind of field where we'll look at the timing of maxima and minima of the black line and compare that to the red and the blue. See which one has the least error in terms of maxima and minima time. So first of all, let's look at this error magnitude, this comparison of the mean absolute error. So we're calling this the ratio, where we have the MAE of this adiabatic plus SST parameterization, comparing that with just the SST parameterization. And if this is less than 1, that means the adiabatic enhanced parameterization is the better one. If it's greater than 1, then just the SST is the better parameterization. But the results are that it's less than 1 in all different locations across the tropical Pacific. And so that's a pretty clear consensus that the adiabatic enhanced parameterization is a better reflection of the air temperature. The timing of the maximum. So the equation here is explaining that. It's the maximum temperature time error for the adiabatic parameterization minus the timing error for the SST parameterization. And again, now this negative value means the adiabatic enhanced parameterization is better. And it is negative in most places, not quite all this time. There's a few locations, particularly in the southeast tropical Pacific, that have positive values, but on average, it's negative, and with a mean of minus 0.69 hours. So the maximum, the adiabatic enhanced parameterization has a better handle on the time of the maximum air temperature. For the minimum temperature, it's the same kind of equation in this case, and this time it's a bigger, a more notable result, the average difference is minus 4.4 hours, and it's all locations except one have a negative value. So again, this is a very significant difference, that the adiabatic parameterization is significantly better when it comes to the timing of the minimum air temperature. So that's kind of the focus on just the air temperature. And so just quickly summarizing that, we kind of find that the model's air temperature field is more closely related to the combination of SST plus adiabatic response to the pressure field. That combination is better than just assuming the air temperature varies with the SST. And next, we're going to look at other fields in the marine atmospheric boundary layer and surface fluxes. How are we doing for time? Okay, good. So just as a kind of general explainer on flux calculations in ocean models. So a flux of a quantity y from ocean to atmosphere can be thought of, or can be calculated as a drag coefficient multiplied by the wind speed and by the sea to air difference in the quantity. So the kind of the gradient across the air-sea boundary. So the drag coefficient is dependent on the atmospheric stability, which is mostly the air-sea temperature difference, the quantity we looked at earlier on. But there's other physics in there too, lots of different formulations, parameterizations of this drag coefficient, still an active area of development. The wind speed, it's pretty simple idea, but it should be noted that it's actually relative to the ocean surface current, not just the pure wind speed. And then this gradient quantity can be a temperature for sensible heat flux, or humidity for latent heat flux, or whatever else for different fluxes of different materials, different matter. So that's the kind of the general idea of a bulk flux algorithm. So let's break this down for the sensible heat flux, where we'll have the drag coefficient, which we're going to mostly look at the SST minus MAT difference to represent that stability component of the drag coefficient. We'll look at the wind speed, and then we'll look again that the gradient is the same quantity as we're looking at for the drag coefficient. So we already saw the SST minus MAT that has that very consistent semi-diurnal cycle of peak values at 3 a.m. and 3 p.m. and minimum at 9 a.m. and 9 p.m. The wind speed on the, oh, sorry, I just went through that. There it is. The wind speed, on the other hand, has minima at 3 a.m. and 3 p.m. and maxima at 9 a.m. and 9 p.m. And is a little bit more noisy. It's not quite as consistent as some other fields we've seen, but on average, it's still a pretty consistent semi-diurnal cycle. And the magnitude of it is not particularly large. So if we just go back and think about the magnitude of this air-sea temperature difference, that's varying on order, like we said, kind of 0.2, 0.3 Kelvin on top of a quantity that's, you know, between minus 0.5 and 1.5. So that's a fairly, it's kind of it can make a significant impact on the absolute value of that gradient. Now the wind speed, the variation here is maybe 0.2 meters per second on a quantity that is probably 5 to 10 meters per second on average. So it's a smaller, proportionally smaller variation, but it is still there, still pretty kind of regular and a consistent variation. And so then the result of combining those in the sensible heat flux here, so this is the diurnal anomaly composite, the sensible heat flux. Now we see maxima at 3 a.m. and 3 p.m. and minima at 9 a.m. and 9 p.m. And so that kind of having it that way around means that it is the stability and the gradient that are dominating this variation. So maxima at 3 and 3, and they're overriding the wind speed variation, which would have minima at 3 and 3. So the wind speed is not really the main control on this sensible heat flux variation. It's more the temperature gradient and the stability effects. And again, the magnitude here is not huge, but the quantity itself is not always that large. So we're looking at around maybe 1 to 2 watts per meter squared variation, but this quantity might not be, on average, might be sort of tens of watts per meter squared. So it's a potentially significant variation. So now we'll turn to latent heat flux. And again, we'll kind of break this down by the different pieces. The drag coefficient, we're going to look at the atmospheric stability, which we've already seen a few times. The wind speed, again, like I said, we're using the same quantity here. And then the humidity gradient is the final piece of that that's new on this slide. And so that is the diurnal variation of the surface humidity minus the 2-meter humidity. Let's look in that a bit more detail at that. So the figures here on the right, the lower right figure, is the diurnal variation of the gradient. So the surface minus 2-meter air value. And I should note that the surface humidity is calculated as the saturated specific humidity at the sea surface temperature. And therefore, its variation follows exactly the SST variation. So I'm not showing that here. You kind of just probably remember what the SST variation looked like, and it will follow the same kind of pattern with a single minima, single maxima, and quite smooth variation between them. And so this kind of this is the dominant part of what's happening in this humidity gradient, that it is mostly, there's a kind of diurnal component maybe superimposed with the semidiurnal variation too, but the diurnal part that's driven by the SST is kind of leading this gradient variation. And if we just look at the 2-meter humidity on its own, it's kind of a little bit of an outlier compared to some of the other fields we've looked at, where it doesn't have kind of perfectly consistent timing in line with the other times of minima and maxima. We saw that this kind of morning minima is a little bit later than we've seen. And then the kind of magnitude as well is some combination of diurnal and semidiurnal. There's a kind of only a minor secondary maxima late morning. So it's not quite varying in the same way as the air temperature as the pressure or the temperature gradient. There's something else must be going on that's affecting the 2-meter humidity. And I'll note that this is the specific humidity. So this is not really taking into account, like a relative humidity would change purely by the temperature, but this having specific humidity here means that there really must be some kind of actual change in the amount of moisture in an air parcel that is behind this. But yeah, in summary, neither the 2-meter humidity nor the air-sea gradient of humidity look like a simple response to the pressure. But they're also not purely diurnal, just like the SST either. There's a complicated combination going on. So how does this look in the latent heat flux? Again, we see a mix of diurnal and semidiurnal components. So probably combining maybe a little bit the wind speed, but more likely the stability, given its magnitude, and the humidity gradient. So again, this, like I said, for the 2-meter humidity, there is some kind of timing here that isn't the same as we saw in other fields. So this morning maximum is kind of between the times we've seen in other fields, and then it pretty quickly transitions to a sort of a minor minimum late morning, late afternoon peak a little bit after the usual peak time, and then it drops off to the evening minimum as well. So one kind of possibility here, which is slightly speculative at this point, is that maybe this latent heat flux variation is what's causing the 2-meter humidity variation from that previous slide with some delay. So the specific humidity in the air is responding to the flux with some kind of integrating delay over time. So that's a kind of intriguing possibility. I don't think we have quite enough evidence to say that is happening. It would need some further investigation, but it could be the case that that's what's happening. And so compared to the temperature, that's a more kind of complicated series of events that causes the variation, where we think from the temperature that seems to be more, it's a kind of easier calculation to do, essentially a simpler schematic of what's happening based on that air pressure variation and the adiabatic temperature response to it. So yeah, I think I'll leave this here. One other thing to note, the magnitude of these variations, maybe sort of 5 to 10 watts per meter squared, it's a little larger than the sensible heat flux variation. But again, this quantity itself is usually quite a lot larger, and therefore in a proportional sense, this may not be as big as the sensible heat flux variation. So yeah, let's see. I'm going to summarize here, and then we can go into some questions and discussion, I hope. But yeah, to summarize, the marine air temperature mean diurnal variation can be considered as a mixture of response to SST and adiabatic response to the S2 atmospheric tide in the air pressure. The SE temperature difference is mostly forced by the S2 atmospheric tide and has a semidiurnal cycle. And this causes a semidiurnal cycle in the sensible heat flux. The variation of the latent heat flux is more complicated. And like I said, I think we need more investigation to really pin down what's happening there. And then the final note is that these results are based on model simulations and theory. We have not got the observations we need to be able to confirm this. So that would be kind of going back to this idea of aspirated versus unaspirated thermometers. If we had a big enough data set of aspirated thermometers, then I'd hope we could begin to see this as we get enough data to kind of have a smooth or good signal to noise ratio. We might be able to begin to pick this out in the results. But again, that needs, I think that needs aspirated thermometers, and that there are technical challenges to do that in the ocean. Yeah, so let me leave it there, and we can take any questions. And yeah, thank you for listening.
All right, thank you for listening, everybody. If you have any question, do go ahead and raise your hands. I'm gonna monitor who does so. If not, I do have a question maybe to start with. You focused on the tropical ocean, and I was wondering if you could give us some insight on what you'd expect in at other latitudes of whether or not you'd see is the same kind of magnitude of impact of the tides, the atmospheric tides.
Yeah, there's a few things going on. So I think first of all, that paper from 1918 notes that you do get the same kind of air pressure variations at other latitudes, but it tends to be swamped by weather systems, essentially. So the day-to-day variations are much bigger, and so you can't really spot the semidiurnal air pressure. But that does mean you potentially can get the same kind of air pressure response to it. But again, it may just be much more harder to pick out given the other variations happening with weather systems in the mid-latitudes and high latitudes. So I think that's one thing. The other kind of thing to consider is that the SST is probably not going to change in the same way. So I think you do get mid-latitude warm layers in the ocean in the summertime. In a few places in the tropics, it can be a year-round phenomenon, but it would be much more of a summertime phenomenon in mid-latitudes, but it tends not to be as large or as regular. Maybe you see it in some coastal regions more, but again, yeah, it's and that is not to say that that doesn't kind of rule out the possibility of the air temperature response, right? That's, like I said, that's not purely driven by the SST, but it's just a kind of another thing to consider, that the dominant processes going on are going to be slightly different.
All right, thank you. We have quite a few questions that lined up. I'll give a word to Shane, if you could.
Hi, Jack. Can you hear me?
I can, yeah. Hi.
Hi. Thank you very much for your talk. That was very interesting. Lots of things I don't know about. So you said it maybe at the beginning, and I was not quite sure. So is the marine air temperature the same type of temperature variable one would get as the 2-meter height temperature over the ocean in a reanalysis product, let's say? Would that be the same variable?
Yes, yeah, nominally that's the same kind of thing. I mean, on a buoy you might see it probably isn't so regularized, but I think it's, you might be a 1 meter air temperature or 3 meters, but roughly speaking, yeah, that is the kind of thing we're talking
And
about. So
so would you expect any reanalysis product or any product providing a 2-meter air temperature to represent this type of semidiurnal variations or not?
it depends a lot on if a model has been used. So I think there's literature out there showing that even models that don't have a very accurate or do not include the stratosphere, they can still have this air pressure semidiurnal cycle. I think there's some kind of compensating error happens with the kind of the lid of the model, so that a lot of climate models, weather models, will have the air pressure that varies in this way, and therefore probably going to have the air temperature varies in this way too.
Okay.
But then that whether there's been kind of filtering and post-processing that's kind of removed it in some sense, maybe that's so. Yeah, I don't want to say it's in all data sets, but there's a good chance it's in most models.
Okay, thanks.
Yeah, thank you.
All right, Dwi, go ahead, ask your question.
Okay, thank you very much. Nice talk, Jack. I have a question. Uh, if I'm not mistaken, you mentioned that the marine air temperature is not from the observation, even though you saw the buoy. I wonder, whether is it from the model or from the buoy, the Togatao buoy?
All the data I showed is from models, but I
Oh, okay.
chose the locations of the buoys to kind of make the calculations and analysis more easy to handle, essentially.
Oh, okay.
Yeah.
Because I thought that you from the Togatao buoy. And then the second, do you have a kind of like a spectra of the SST and then also the marine temperature and so on, so that you can see it, and then whether is it possible that it is ocean tide, not the atmospheric tide, that may cause of this?
We have looked at spectra. Yeah, I think there might be an extra slide that I have it in. Let me just quickly check. No, I don't think I included it. So, but we do have. I have looked at spectra, and you do see pretty well-defined peaks at 12 and 24-hour periods. In terms of the ocean tides being part of this, I think it's hard to kind of say. Well, no, we can rule it out on these kind of longer term averages, because once you take the 30-day or more average across the 24-hour cycle, then the way the ocean like M2 tides, so that 24.8-hour period, once you've gone beyond a certain, roughly a lunar month, then that averages out within the 24-hour period. It kind of cancels itself out. So by looking at anything over 28 days or 30 days or longer, you remove any the dominant kind of ocean tide M2 variations. So just in terms of the calculations, we've kind of that would be averaged out. In terms of physical effects that would cause that, again, I don't really see how that would be kind of impacting the air temperature in this way. But if you have any ideas, then yeah, it'd be great to think about it, because it's a kind of interesting, tides in general are a kind of fascinating subject. So yeah, let me know if you
Okay,
have any
that's right.
thoughts about it.
I put post it in the chat so that you can take a look at this paper.
Okay, I will do. Thank you.
Okay, thank you.
All right, Agostino.
Yes, Thank you very much for the presentation. And you nicely showed us that the surface turbulent fluxes have this diurnal, semi-diurnal variability. So I was wondering if you also looked at the buoyancy of the lower atmosphere. So how this fluxes changes the buoyancy of the air, and how this can potentially change the mixing in the marine atmospheric boundary layer, its thickness, or also impacts on low-level clouds.
I haven't looked at it specifically. I think I would expect to see something in the buoyancy, and I think that's a great insight, because I think there are papers out there that have looked at or found some evidence of semidiurnal variations in precipitation and cloudiness in the tropics. So I think that's yeah, it would be a really interesting thing to look into more. Hopefully this work can kind of inspire some further analysis of that, but we haven't done that at this stage. But yeah, I think that'll be an important kind of pulling multiple different threads together. So
I'm asking because we looked at the spatial variability of SST, and we have seen that this can modulate the mixing and the formation of low-level clouds. So I was wondering if this spatial control can also be can also have an equivalent in time, as you show.
yeah, I would think that would be a good thing to look at. So thank you.
Thanks.
Okay, Sarah, go ahead.
Yeah, really nice talk. Thank you. I wondered, your analysis is based on a bulk parameterization, which I guess is probably what's wired into the model.
Yeah.
But there are questions about whether on a local scale, the fluxes are really driven by the same thing as the bulk parameterization represents, or whether there are other types of processes that might be relevant. Do you have any thoughts on that?
First, I would say that, so I use that formula as a kind of framework to steer the analysis through, but you're right, the model also in the background is using the same kind of idea in its calculations. I think the CFS have the Zhang 98. I can't remember, but yeah, there is a bulk flux formulation in the model. And yeah, I totally take your point that it is a kind of a statistical average across lots of different situations, and so there could be local effects and physics that isn't included in them. I think I saw recently a study that said if you replacing the kind of minimum wind speed in those calculations from say 1 meter per second to 4 meters per second removed some bias in the fluxes. I think so. Yeah, clearly there are ways to, there are things that are not included, or approximations, and I don't really have a good answer to how to kind of get at those, but I think it is a thing to look at, think about more, and maybe, I guess there are not very many, but there are sensors out there doing eddy covariance measurements that could be used to kind of look at that, look at the flux variation in conjunction with these effects. So that would be an interesting thing to look at.
Absolutely.
Yeah.
All
But thank
right,
you. Good question.
Hi, Jack. Great stuff. This is really cool stuff. Love to see it. I have a thought on, or rather, want to get your thoughts on how you think that this could be height dependent as well. Like if you're looking at ships versus USVs, for example, if you were to see a bigger amplitude for closer to the surface, or at 20 meters of a research vessel, if you had any thoughts or looked into that in any way.
Great question. Yeah, I haven't really thought about that, looked into it much. I mean, the air pressure, I think, would be that would be consistent across heights, some minuscule kind of differences across those few meters, but I think that would be pretty consistent, and therefore the adiabatic component would be pretty consistent. Again, my sense, this is just a guess rather than anything like particularly scientific, but I think the SST influence would be kind of similar across that range. I think it's with a ship, there's always just kind of such a potential for biases there just from the surroundings. That's going to be hard to work around, but yeah, it's a good question though. I think it's kind of interesting to think, like I alluded to with the latent heat flux, kind of looking in more detail at the processes and like the model tendencies from different layers in the model might kind of help to understand this a little more. But yeah, I don't really have a good answer, but other than thinking it'd be mostly consistent across, 2 meters to 20 meters is probably going to be quite consistent. Maybe if you go up to 200 meters, then other effects start to become involved, and it's much more than the kind of the boundary layer as a whole rather than the surface layer.
Okay, great. Thanks.
Yeah.
All right. Any more question from the public? If not, I suggest we thank Jack again for this great talk. Very interesting. And
Well, thank you. Thank you for the opportunity and for the great questions too. So I really appreciate it.
Sure. Just as a reminder, there'll be another webinar next week. All right. Bye, everyone.
Thanks, everyone.